Dear students, and the next topic is the examples of simple harmonic oscillators. And the first example is a simple pendulum. A simple pendulum, it consists of a heavy bob, ideally a point mass, suspended by an inextensible weightless string from a point in a rigid support. And a compound pendulum, it is a rigid body which is capable of oscillating freely about a horizontal axis passing through it. And the third one is a torsion pendulum. A torsion pendulum, it consists of a heavy mass suspended by a thin wire from a rigid support. Normally, the heavy mass is a disc or a spherical bob. And the fourth one is a loaded spring or a spring mass system. It consists of a massless spring suspended vertically from a rigid support having a body of mass m attached to its free end. And today we are going to study an expression for the time period of oscillation of a simple pendulum. A simple pendulum consists of a heavy particle, ideally a point mass, suspended by an inextensible weightless string from a point in a rigid support. And the point from which the bob is suspended is called the point of suspension of the pendulum. And the center of gravity of the bob is called the center of oscillation. And then the distance between the point of suspension and the center of oscillation is called the length of the pendulum, and it is represented by L. And consider the expression for the period of oscillation of a simple pendulum. For that, consider a simple pendulum in which S is the point of suspension and A is the equilibrium position or mean position of the bob. And the distance between S and A is called the length of the pendulum and is represented by L. And if the body is drawn to one side and let it free, it begins to oscillate about a mean position A. And this oscillation can be represented by this dotted line. Let theta be the angular displacement at any time t, and if m is the mass of the bob, then at the mean position, the weight of the bob which is acting vertically downward, and the tension in the string, it is acting vertically upward direction. That is, at this point, both the weight and the tension, they are equal and opposite, and hence the point A is at the equilibrium position. Then at the extreme point B, at this point, the weight of the bob mg, which is acting vertically downward, and this weight, it can be resolved into two components, and one is the mg cos theta, another one is mg sin theta. And in the diagram, consider the line SA, and this line, it is parallel to this line. Therefore, this angle is theta, and hence this angle will be theta. And therefore, this component of force, that will be mg cos theta, and this component will be mg sin theta. Here, the component of force mg cos theta, it balances with the tension in the string, and hence it is a balanced force. But the mg sin theta, it is an unbalanced force, and the effect of this unbalanced force is to produce an acceleration of the body. And because of this unbalanced force or this unbalanced component of this weight mg, this body, it tends to comes to its mean position. Let x be the displacement from the mean position. And we have studied the expression for the potential energy and kinetic energy of a simple harmonic oscillator. And we know that the potential energy is maximum at the extreme position and minimum at the mean position. But the kinetic energy is maximum at the extreme position but minimum at the the kinetic energy is maximum at the mean position but minimum at the extreme position. That is, the velocity of a particle, it is 0 at the extreme position, and as the body moves towards the mean position, its velocity increases, and when it reaches at the mean position, its velocity becomes maximum. And then because of the inertia of the velocity, this body, it overshoots the mean position and it goes to the extreme position. And again, when the body just passes the mean position, its velocity starts to decreases, and at the extreme position it becomes 0. Again, because of the restoring force, it has a tendency to come to this mean position. And during that time, then its velocity again starts to increase from the extreme position to the mean position. At the same time, the acceleration, it decreases from this extreme position to the mean position. Sorry, the velocity, it increases from the extreme position to the mean position, but the acceleration, it increases from the mean position to this extreme position. And then again at the mean position, because of the property of the inertia of the velocity, it again goes to the other extreme position. That is, in the case of a simple harmonic motion or a oscillatory motion, the inertia and the restoring force are the two important factors which determines the oscillation of the body. And because of inertia and the restoring force, the body executes an oscillatory motion. That is, the velocity is 0 at the extreme position and maximum at the mean position. But the acceleration, it is maximum at the extreme position but 0 at the mean position. Here we are considering the component of the force, that is the unbalanced force. This unbalanced force can be represented as F is equal to minus mg sin theta. And here the value of the theta, it is the angular displacement, and it is very small, hence we can approximate the sin theta is equal to theta. Therefore, the force can be represented as minus mg theta. But from the figure, the theta can be represented as, theta means this is the angle theta, and this side gives the length L, and the distance x can be represented as this value. We know that this arc by radius is equal to angle. That is angle. Here the angle theta can be represented as, theta is equal to, the arc will be the x and the radius is L. Therefore, we can write theta is equal to x divided by L. That is, the force can be represented as minus mg x divided by L. Or from this equation, we can see that the force F will be proportional to minus x, because this value, that is mg by L, for a given body the mass is a constant and the gravity is a constant, and for a given pendulum L is a constant. Therefore, the force will be proportional to minus x. That means the force will be proportional to the displacement x from the mean position and is acting opposite to the direction in which the displacement takes place. That is, this is the condition for simple harmonic motion. And from this equation, that is F is equal to minus mg by Lx, substitute the value of F is equal to ma, that is from Newton's second law. That is, then the equation becomes ma is equal to minus mg by L into x, or the a can be represented as minus g by L into x, or the a by x, that is the acceleration per unit displacement, can be represented as minus g by L. And consider the expression for the period t is equal to 2 pi divided by omega. And but omega, we know that the omega means omega is equal to the square root of the acceleration per unit displacement, that is root of a by x. Therefore, time period t can be represented as 2 pi divided by root of a by x, or from this equation the a by x can be represented as g by L in magnitude, that is t is equal to 2 pi into root of L divided by g. That is the expression for the time period of oscillation of a simple pendulum. T is equal to 2 pi into root of L by g. That is, let S be the point of suspension of the pendulum and A be the mean or equilibrium position of the bob. At the point A, the weight of the bob acts vertically downwards and the tension in the string acts vertically upward. These two forces are equal and opposite, so A is the equilibrium position. On taking the bob a little to one side and then releasing it, the pendulum starts oscillating about its mean position. At a given instant, let theta be the angular displacement at any time t. If L is the length of the pendulum and m the mass of the bob, then the weight mg is resolved into two rectangular components. The component mg cos theta acts radially along SB and is equal and opposite to the tension in the string. The component mg sin theta acts tangentially along BA and this acts towards the equilibrium position and hence it is called a restoring force. But this restoring force can be represented as minus mg sin theta. Therefore, and sin theta is approximately equal to theta. Then from the figure, theta can be represented as x by L. That is, the angle is equal to arc by radius. But f is equal to minus mg x by L, or ma is equal to minus mg x by L, or a can be written as minus g x by L, or the acceleration per unit displacement a by x is equal to minus g by L. That is, the period t can be written as 2 pi by omega. 2 pi divided by omega is a root of acceleration per unit displacement. That will give 2 pi divided by root of g by L, or the period t can be represented as 2 pi into root of L by g. And this is the expression for the period of oscillation of a simple pendulum. And we can see that the period, it depends only on the length, and the 2 pi is a constant and the gravity g can be represented as a constant, then it depends on L. That is, it does not depend on mass. If you are using two pendulums having different masses, then the period will be the same. And if we are using two pendulums having the same mass, and then if we oscillate these two pendulum, and the one of the pendulum, it produces an oscillation up to this point, and other pendulum which produces an oscillation up to this region. That is, for the first pendulum the oscillation is T1, and for the second pendulum the oscillation is T2. But these two pendulum having the same length, then the T1 will be equal to T2, because the period, it depends on the length only. It does not depend on the number of oscillation. That is, if the two body having the same mass or different mass but having the same length, but it have two different number of oscillations, then the time period will be same. That is the expression that is the equation t is equal to 2 pi into root of L by g. Next is the drawbacks of simple pendulum. And this simple pendulum, it is used for the determination of the value of acceleration due to gravity at a place. But this simple pendulum, it suffers from a number of drawbacks. And some of the drawbacks are, the first one is the motion of the simple pendulum the motion of the bob is not strictly linear. It has a rotatory motion about the axis of suspension. And the second drawback is that the expression for the time period is true only for oscillations of infinitely small amplitude, because we are considering the angular displacement theta as very small. And the third one is the bob has a relative motion with respect to the string at the extremities of its amplitude on either side. And the fourth one is the resistance and the buoyancy of the air affect the motion of the bob, but we are not considering these effects during the experiment. And the simple pendulum is an ideal concept, since it is impossible to have both a point mass and a weightless string, so that the string too has a moment of inertia about the axis of suspension. And for all these reasons, a compound pendulum is preferred to a simple pendulum for the determination of the value of the acceleration due to gravity at a place. And in the next class, we will study the compound pendulum.